Welcome back to 3 Inquisitive Kids. Today we're going to be looking at geometry, but the figures that we are looking at here are going to be 3D. So we're going to be working with not just surface area and side lengths, but we're also going to be looking at volume. The two cones shown have parallel bases and a common apex T. TW is 32 meters, WV is 8 meters, and ZY is 5 meters. What is the volume of the frustum with circle W and circle Z as its bases? Express your answer in terms of pi. We are trying to find the volume of this shape down here. So a cone with a cut-off top, or you could think of it almost like a 3D version of a trapezoid. So we're trying to find the volume of this. And in order to find the volume of that, we need to know two things. We could find the volume of the total cone, and then find the volume of just the top cone, and then subtract. So I think that's a good way to start. And now let's label what we know. So they have a common apex T, so that's the tip. TW is 32. So the height of the large cone is 32 meters. So this is 32. WV is 8 meters. So the radius of the big cone is 8 meters. And ZY, which is the small radius, is 5 meters. How can we find the respective volumes of the small and the big cones? Well, when solving for the volume of a cone, we need multiple things. So we are multiplying 1/3 to the radius squared times pi times the height. So this part is really just a cylinder, and then we take 1/3 of that cylinder. So that's how we find the volume of a cone. Now let's think about what we know. Well, we do know that the radius is respectively 5 and 8, but we also need to find the height. We know that their total height is 32, but apart from that, we don't really know their actual height. So the first step is to find the height of individual cones. So how do we find the height? In 3D geometry, just like in 2D geometry, sometimes we can use ratios, and we can find similar shapes if we see that they are just a dilated version of one another. Here, we can see that the small cone and the big cone are actually similar, because they share the same apex and their sides are completely overlapping each other. So it's almost as if we zoomed out the small cone to make the big cone. So we know that there is a similarity, there is a scale between the small cone and the big cone. But what is the scale? What is the scale factor? How can we find the scale factor? Well, we can do that by comparing their radiuses, which we already know. We know that if we were to compare the two cones, in all of their parameters, it would be 5 to 8, with 5 being the smaller cone and 8 being the larger cone. This is the same in all parameters, such as height, radius, and volume. So we know that if we were looking at this in terms of height, we could set the height of the small cone, which is TZ, as 5a, and we'll set ZW as 3a. This means that the total height for the big cone is 8a. And now let's think about it. 5a plus 3a, you can see this very clearly visually, is equal to 32 meters. So 8a is equal to 32. That means that a is equal to 4. So we know that 4 is a. So if we substitute this back in, we know that 5a is 20 and 3a is 12. Now we can easily find the volumes of the cones. So the volume of the small cone is, just substituting into the formula, is 1/3 times 5 squared times pi times 20. So this gives us 1/3 times 500 pi. So 500 over 3 pi. And now let's look at the big cone. Well, by looking at the big cone, we know it's 1/3 times 8 squared times pi times the height, which is 32. So we have 1/3 times 64 times 32, and that gives us 2048 times pi. So this equals 2048 thirds pi. And now we're supposed to subtract. So we have 2048 over 3 minus 500 over 3 times pi. And this will then turn into 1548 over 3 pi. And this is simplified as 516 pi. So our final answer is 516 pi meters cubed. Don't forget the unit there because it is in cubic meters. As you can see, the big part of solving this problem, the key to solving this problem was to find similar ratios. We had to identify similarity and then identify the scale factor or the ratio that it was scaled by. So again, just in 2D geometry, where we often use ratios to determine similarity, we use this commonly in 3D geometry as well. That is the end of this video. See you next time.